Okay, at this part we will introduce RF basics. And firstly, let's see the radio wave. It's an energy transmission form. During transmission, the electrical field and the magnetic field are vertically to each other in space, and both of them are vertically to the transmission direction. So as you see in this picture, this is a radio wave. And about the radio wave, here it shows us two features. First is wavelength, and next is velocity, actually the speed, how it transmits in the air. Okay, after introducing the radio waves, next let's see what is RF. Radio frequency, RF, indicates the frequency of electromagnetic waves radiated into space. The frequency ranges from 300,000 Hz to about 300 GHz. RF is abbreviation of high frequency or AC change electromagnetic waves. AC change less than 1,000 times per second is low frequency current, while if it changes greater than 10,000 times per second, this is high frequency current. And RF is a high frequency current. About the RF, here it shows us some features. First is a wavelength, which we just introduced at the last page. It indicates the transmission distance of RF signals in a period. For example, in this picture, here is a wavelength period. And next is frequency. Frequency indicates the number of times that a specific event is repeated at an interval in Hertz. But for the RF, the frequency means radio wave repeats. And normally we use Hertz to distinguish them, high frequency or low frequency. Okay. Next is amplitude, where the signal strength or power. And in this picture, you can also see what's amplitude of it. Next feature is path, position relationship between two intra-frequency signals. When the path difference is 0, the signal strength increases, while when the path difference is greater than 180, signals are offset. Okay, and wavelength is inversely proportional to frequency. A higher frequency indicates a shorter wavelength and faster attenuation through different media. So this is also the reason why we see that 5 GHz signals have a smaller coverage than 2.4 GHz signals. Okay, this is about the RF. And next is about the transmission of it. In RF communications, one device sends vibration signals, and another device or even multiple devices can receive it. These vibration signals are based on one constant. It's called the frequency. The transmitter uses a fixed frequency to send signals, and the receiver is adjusted to the same frequency so that they can receive it. For example, in this picture, you can see on the left is a transmitter. Right, it's using the antenna to send out signals, and of course, the antenna of the receiver will be adjusted to the same frequency so that we can receive the signals from the transmitter. This is about the transmission. And next, let's see the RF. Actually, based on their frequency, we can distinguish them into different types. For example, as you can see, VLF, right, ultra long wave, which frequency ranges from 3 to 30 kHz, right, and its wavelength ranges from 10 to 100 kilometers. It's quite a long distance. And the main application of it is about, for example, navigation or sonar. And except that LF, MF, HF. Actually, you don't need to remember the exact number of each type, but actually from this table we can figure out that the higher the frequency is, for example, from 3 to 30 kthousands to maybe 3 to 30 GHz, the frequency is quite high, but we can see that the wavelength range is shorter and shorter, from maybe 10 to 100 kilometer to even 1 to 10 cm, right? Or even 1 to 10 micrometer. This is about the distribution of the waves. And about different types of waves, let's see, the WLAN signal. We all know that the WLAN signal uses 2.4 gigahertz or 5 gigahertz frequency. And you can see we have distinguished them into super high or ultra high type. And about the RF transmission, there are different types of behaviors. Let's see it. Signals are related, scattered, diffracted, or refracted during transmission. The signals arriving at the receiving end are generally the coupling of multiple signals with different amplitudes and phases. So what kind of behaviors would happen during the transmission of the RF waves or of the signals? Let's see it. First is called the straight line. Actually, in this picture, you can see the number 1 arrow. It means that the receiver is directly or straightly receiving a signal from the source, right? So this is a very common behavior called the straight line. And next is reflecting. Let's see the number 2 arrow. This is a signal from the source. Actually, this signal is reflected by the building here. You can see the direction has been changed. So when an electromagnetic wave encounters an object larger than the wave, reflection occurs. So this is a situation that we can see from arrow 2. And next is called diffraction. When an electromagnetic wave is blocked by an object nearly the CMS or smaller than the wave bypasses the object. Okay, the last is called scattering. Tiny particles in the medium change the origin direction of an electromagnetic wave and spread it to all directions. Okay, for example, number 3 and number 4. The directions has changed, and it could be maybe a scattered wave or diffracted wave. But the difference between them and in which situation will cause maybe diffraction, refraction, or scattering. So we will see them one by one. First is reflection. This is very easy to understand, so let's see it together. Reflection is one of the most important RF propagation behaviors. When an RF wave hits a smooth object, pay attention here, a smooth object. For example, the surface of a water, right, is smooth, or if it's a metal door, it's smooth, and the direction will be changed. This is called reflection. For example, in this picture, the antenna sent out a signal, and the signal has been reflected by this surface. It could be maybe water surface, or it could be some other objects. And the direction has changed. So this is called reflection. And if for the indoor objects, for example, fire cabinets, the metal doors, or even a wall would cause reflection. But for an outdoor, it could be maybe a water surface, right? Or the atmosphere would cause reflection. Okay, after understanding the reflection, next, let's see the diffraction. Diffraction indicates that the transmission direction and the speed. So not just the direction, even the speed of the RF signals are changed when they pass through the edge or a split of an obstacle during transmission. For example, you can see here the antenna sent out two signals, and when Z meets the building here, firstly they have changed their directions, right? The direction has been changed, and maybe they have also already changed their speed. Diffraction indicates that the RF signals deflect around an object. Pay attention here, around. Okay. Next, let's see is scattering. Scattering can be divided into two types. Type 1, let's see it. The waves are reflected by a tiny particles, such as, for example, smoke, fog, or even a sand. The impact on signal quality and the strength is small. From here, actually, we can find that scattering may affect the quality and the strength of the wave, but for type 1 scattering, the impact is small. But for the type 2 scattering, let's see, a main signal propagated to a rough surface, such as maybe a wire fence, a leaf. For example, in this case, let's see, this is a signal, and the signal is scattered, for example, by the rocks on the roads, right? And it has been divided into different directions. And if in this situation, it will cause quality deterioration of main signal and even destroy the received signals. So the impact is huge. Okay, this is called scattering. Okay, next is refraction. RF signals also deflect, which is known as refraction. For example, when they are transmitted in the air, for example, if it's a cold air or it is humid air, the result would be different. An RF signal deflects when it passes through a medium of varying density, resulting in a change in the direction of wave propagation under the atmospheric effects. RF refraction often occurs and has a great impact on outdoor projects. You can see here, even if they are transferred in the air, if it's a cold air, firstly the direction has been changed. But if it's a humid air, the direction also changed, but the result is different, right? So it's impacted by a lot of situations, a lot of maybe parameters during the transmission. Okay, this is about the refraction. And next, let's see multipath. Multipath transmission easily generates multipath interference, because in this picture we can find that from the AP to the PC to the client, actually there are three types of paths of the signals, right? And it means that when the PC receives the signals, there are three different signals, right? And then the PC will stack them. After stacking, actually, we can find that it have already caused the interference between these three signals, and it will affect the performance of the wireless network, especially for 802.11 ABG WLAN. And next is about the absorption. Here in this table, it shows us that, for example, a 4.5 centimeter thick metal door will cause 13 dB attenuation to the signal. While if it's maybe 45 centimeter thick concrete wall, it will cause 18 dB attenuation to the signals. While when the thickness is higher, for example, 70 centimeter thick concrete outer wall, it will maybe bring 45 dB attenuation to the signal. So from here, we know that the thickness of the material, and of course include the type of the material, will affect how much attenuation it will bring, right, to the signals. And next, let's see the relationship between absorption and object thickness. From the last page, we know that The more higher the thickness is, maybe the more absorption will cause to the signals, right? So it says that a small amplitude indicates weaker energy. Signals will be absorbed when they pass through water. And of course, water is contained maybe in human bodies. So when the signal maybe goes through or transfers through human bodies, some of the signals will be absorbed by maybe our human body. And the human body absorbs signals in dense areas such as maybe stadiums, maybe exhibition centers. So when we design a wireless network for this kind of areas, we should take the human body into consideration. Okay. And you can see that when the signal goes through an object, you can see the amplitude has been reduced. Right? It means the power has been reduced. Some of them are absorbed by this object. And next, let's see, it shows us different type of obstacles have different attenuation levels. For example, if it's an open space, the attenuation is extremely low. While if it's human body, the level is medium. And if it's a paper, it's high. And if it's a metal or maybe silver plated material, the attenuation is very high. So no matter when we design a wireless network or during the use of it, we should take this kind of maybe objects into consideration to improve the user experience of the network. And next, let's see the attenuation. In addition to the attenuation caused by obstacles, by absorption, by reflection, and so on, the RF signals also attenuate due to transmission. Because theoretically, RF signals can be transmitted permanently, but actually, in fact, it's not. Right? It's obvious because during the transmission of it, at least it should go through the air, and some of the power will be absorbed or it will be turned into maybe heat. Right? In this way, it will be affected during the transmission process. Okay, and next is about the relationship between rate and distance. Since we said that some of the power, right, some power of the signals will be absorbed during the transmission of the signal. So from this point, we can understand that by the increases of the distance, it would bring some loss of the power. And when we see the relationship between rate and distance, we can also see that with an increase of distance, maybe the rate is becoming lower and lower. The maximum coverage varies depending on the environment. Is an maybe open space, or is there any objects would cause a huge impact of the signals, right? And coverage is also related to the antenna type and maybe the transmit power. Actually, from these parts, if you want an AP, for example, to cover a large area, we can adjust the antenna type or we can adjust the transmit power, right, to make it maybe larger or to make it smaller. But here you should pay attention. It's not fixed that the coverage is not the larger the better. Okay. In the maybe following course, we will introduce the reason why it's not. Okay. And next, let's see the electromagnetic interference. In the first part of this course, we have mentioned it about the interference. Because 2.4 gigahertz and 5.8 gigahertz are SMB bands, you can use it freely. So, for example, no matter microwave, no matter some bidirectional paging systems, right, maybe some other applications are using this band, it brings the interference, right? And interference deteriorates the overall system performance or even core system malfunction. And This tells us that we should pay attention to the interference. Maybe when we do the network optimization, we should find out if is there any interference in the network, or how can we avoid interferences in the network. Okay, and next is about RF GAN. Because if we want to make, for example, we want to make the coverage larger, or we want to improve the strength of the signals, it will help. And the RF GAN can be divided into active and passive. Let's see. First, the active GAN is an amplifier is maybe installed between the transmitter and the antenna to amplify the transmitting and receiving signals. Active GAN requires an external power supply because we should use its power to amplify the signals. But for the passive GAN, an antenna is used to centralize the signal. We do not maybe amplify it, we just centralize it to maybe specific direction. An antenna is a passive device and does not need external power supply. An antenna can centralize signals in a direction. So this is about the RF GAN, which is active, which is passive. You should know the difference between them. Okay, that's all for this part, and let's see a question. In this way, we can do a summary together. Which of the following obstacle causes highest attenuation to the signals? A is wooden objects, B is human body, C paper, D metal. I think for you this is quite easy, right? We choose D. Metal brings highest attenuation to the signal. Okay, that's all for this part.